Okay, let's start with the uh, with some exercise in what's it called in Riemann sum, all those kind of problem. Okay. Okay, let's pick up some problems. Where is that thing? Okay, so let's do this one here. Okay, have you seen what I'm sharing with you? From the textbook.
Yes, sir.
Oh, okay. All right, so let's see. Um, say number 7 and 8. How does it differ? 7, 8, since I would like to. Okay, so this type of problem. So the question is as follows. This limit represent an integral. Okay. Uh, limit represent an, a definite integral. So this limit here. So the question is how to find and A and B. Okay. Right, so to be able to recognize this limit as the limit of Riemann sum. So that's the questions. Okay. Okay, so the we did a couple of times writing integral as a limit of Riemann sum. Now the the other directions. Given the limit, what is the function to be integrated? Okay, so the easiest one first, number 7. Okay, so we have this limit here. I don't rewrite this, don't need to rewrite. Okay, this is A and B's are already given. Okay, so we need just to find the A though. This is given. Just need to find F. Okay, so let's see how we do this one. So we need a subdivision of interval from A to B from 1 to 3. So this from 1 to 3. So length 2. Okay, and divide into n parts because you look at the summations. Okay, so this tells you divides to n subpartitions. Okay, so how to do this one? Yeah, defined. Because this is 1 plus 2 over n. Why 2 over n? Because this length 2. This one is 1 plus, sorry, yeah, 4 over n. Okay, and this one is 1 plus 6 over n, and so on. Okay, so the general thing is that, oh, sorry, this is x naught, x1, x2, x3, and so on. So xk or xi is, let's see, 1 plus, okay, what's the formula you think? 1 plus what? What is the formula for xi? This is x1, this is x2, this is x3. So what is xi?
Is it 3i over n? 1 plus 3i over n?
So 3,
I mean 2i, 2i.
right, all right, good. There we go. So I starts from 0 till uh, yes, and okay, so this is what we have. Okay, so what we have in this one here. So here, what we have is that it's x. Let's see, what is this? What this? Let's see. Let me get what this bar means. Okay, yes, let's see if any. Yeah, that's okay. That's fine. Okay, so let's see. Or try to find out what X bar is. Okay, so this. Okay, so this is just limit. See, oh, then that's, we don't need this one actually. All right, just let's write this down. Okay, so this is just a um, we don't need this one. So this limit is just the integral of from 1 to 3, right? So it's given already. What is this one? Yeah. Okay, so just this is just the f of x. We don't need that one actually. Okay. So this is what it means. We Don't actually need this one. Right? Later on, we use this. Okay. All right. Let's say, so what is number 10? Number 10, that's easy also. Sine of x, the square is the whole thing. Okay, so this is nothing but, this is I from 1 to n. Let's see, this is given, but this would be just sine x squared dx. That's questions. Okay, if not, then okay. So let's do, for example, this one. For example, this one. Okay. What it says is use geometric intuition, geometric reasoning for this one. All right. So what we do is try to picture this problem. So that's what we compute is area under the curve. Okay. So we'll see what we get here. This is a square of uh, round down. Okay. Recall that the okay. So you would like to find uh, you round down x and then you square it and then you find the so what we do here is try to picture this first. This one. So what we have is that say 1, 2, 3, 1, 2, 3. Okay, so everything which is round down to 0 is this one. Now I don't care much about the boundaries, the borders. Okay, here you have yeah, that's- here you round down. This one and okay. So that is a round down of the what do you call it? Uh, Bracket functions, round down. Okay. Let's see. Then you square it. If you square it, the negative become positive. So this is -1, -2, -3. Okay, so here remains 0. Here becomes, oh, it remains 1. Here becomes 4. Okay, so this is what you have. And sorry. Okay, so this is, oh yeah, I need to put this down. Okay, so this is 1, 2, 3, 1, -2, -3. Okay, so here's the value is 0. Here's the value is 4. 1, 2, 3, 4. Okay, this is 1. And this is 2 becomes 4. Uh, 1, 4. 1, 2, 3, 4. All right, here. Okay. And here, because this -1, it's 1. Square it. -2 become 4. Right? And here, -3 squared becomes 9. 4, 5, 6, 7, 8, 9 here. Let's sorry. Oh, okay, it's um, okay. Here. Okay. So when you integrate, what we are looking at is actually this area here. Okay. 0. This. Yeah. Okay. So then that's easy. This is 9. This is 4. This is 1. Okay. So this integral is equals you add them up. Okay. So 4 is 4. It's just 1. That's 0. This is 1. And then 4. And then 9. Okay, so that's the integral. So if you compute 5, 6, 10, 19. Okay. So far, that's how we calculate integrals. Okay, so let's move. Oops. I lost this is the step here. Okay, let's do some of this one now. Okay, so let's do not all, but a couple of things from here. Okay. All right. Okay, let f be odd functions, g be even functions. And suppose the integral is the same here, absolute value of f, and g is 3. Now use geometric reasoning to calculate each of the following. Okay, so let's see. A. Let's do the A. A here is the absolute value. Okay, from 1 to 1. Okay, so what we have here so far. I should just think first before this problems. Uh, let's do some properties of definite interval. Okay, first is that uh, if you have these additions, then you can compute each of the integral. And if you multiply this f first and then integrate, that's the same as compute this integral, and then take the scalar out, the coefficient out. Okay, so this is called linearity, and then you can do this one also. Okay, so if that, oh, sorry. Um, uh, not from A to B, but B to A. Okay. If you replace switch the order of the boundaries, the bound for integral, and then like this, we have this negative sign. Okay. And then the fourth one is that here. Um, if you have this one, then you can compute from A to C first, and then from C to B. Okay. I won't prove this one, but just we will use them. So this one says that we have something like this. Say A to B. You can split this from two. So you compute this integral here, and then you get the whole thing from A to B. Okay. So this one, say the additive properties, additive properties of definite integral. Okay. So that's the properties that we will use. All right, so let's go back to this one here. Okay, so A from -1 to 1. Okay, so what we have here. Okay, the data is about from 0 to 1. Okay, so let's split it to this one. It's from 1 to 0 and from 0 to 1. All right. Okay. Since we know that the, let's see, the data is about this one. Okay, but this is, let me check. Without this. Okay, I'll do C first. Okay, because okay, so here's the, this is 3 because it's given. All right, so what about this one here? From 0 to 1. All right, since we know that this is a f is an odd functions. What is odd functions? Remember that odd functions, meaning that if you compute this one minus x, then you get this. Okay. So the value of f at the negative is the same as the, say, the negative of the positive one. So you example, and then you have, let's see, count this. Oh, yeah. Okay. This is the odd functions. But then you take the absolute value. Okay. If you take the absolute value, so you have okay, take absolute value, then it becomes f of x. Is this one. Okay. So when x is negative, so you have also this one. So this is the same as the so this is 3. Okay. Okay, so that's the functions. Okay. And let's see here. What about this one here? G. So say B. Uh, 1 to 1 G of X. And we do the same thing here. Split to from 0 to 1, negative 1, and from 0 to 1. All right. So this one, we know this should be 3. Okay. And this one, well, because G is now an even functions, meaning if you have even functions, if you have this one, and then just copy this one to the even. So just turn it around and then you have this one. Or you can just say reflect. So of course this has the uh, same area. So it is going to be 3 also. 6. Okay. All right. So let's see. Now the interesting thing about even and odd is this one. Say it is an odd functions. This integral is going to be 0. Why? Because you have this one. If you have there something like this, say this is A, this is minus A. This picture is going to be something that looks like this one. Okay. So this integral and this integral is this. The area is the same as this. This area is same as this. This is same as this one. The only thing is that they differ by sign. This positive, negative, this negative, this positive. So that's why this is the 0 is the negative. Okay. So when you add them up together, you add them from negative A to 0 in this, what you get is 0. Okay. But if you have an even functions, and you compute this one from A to A, what you get is, if you compare it to This is only one half of this, so this is just twice. See? So because of the geometry. So that's what I remark from those problems. Okay. All right. So let's move on to the next sections. All right. So, okay. Questions so far? All right. So the question of fundamental theorem calculus is the thing that relates um, definite integral, indefinite integral, derivative, uh, yeah, derivative. Okay, so because calculus is both integral derivatives, this is called fundamental, the key thing about the calculus. All right, let's see this one. Okay, so that's the fundamental of the calculus. First one say that I guess take where is that thing? Okay, okay. First one. Sorry, like this. All right. Okay, so this is the fundamental calculus. So we're talking about continuous functions on this closed interval. Uh, say this is a point in. Then we have this one here. Okay. So if you take derivative of this one here. So the thing here is that um, uh, this is just a number, right? Why we take derivative of a number? But in fact, let's see. This is a variable there. Okay. So let's. So if you compute from A to B, you can use X, you can use T, you can use whatever letter here. Okay. So that means you're computing, say, this area here, right? But the thing here is that you compute this area. Okay. What is now the from A to X? So that's the reason I use T here, because I don't want the variables is in conflict with this X. The picture looks like this one here. So, for example, we can. So this is A, still A. This is just X now. And X can move around. So this, the area, this is this area. But then you can move X to the right or to the left, because this X is variable. So vary the X, left and right. Okay. So that's why then we have, we can say that let Fx to be capital F. There. Okay, so this become functions. So this express the area of under F, under curve F, from A to X. Thank you. That's a function. All right, so fundamental theorem of calculus says that if you compute the derivative, this equals to, if you take the derivative of A to X, so meaning that this mx should be dx derivative of, okay, so that means prime, that's equal to f itself. Okay, so you start with f, you integrate, and you take derivative, you end up with f. Okay, so what we have is that f, you take the derivative, so it becomes integral from a to x, f to t, and then you take derivative, and suddenly it comes. Okay, so meaning that, but t and x are just dummy variables. What's it called dummy? Well, it doesn't matter. You call it x, you call it t, or call it u, or whatever. That's the same thing. We call it a function is a rule. So changing the variable doesn't change the rule. So in this case, uh, you see that this integral in this particular form and derivative is inverse to each other. Okay, so in this sense, c and d dx are inverse each other. Okay, so this fundamental theorem of calculus answer the question whether can we find an inverse to that to a derivative. Yes, we can. The the inverse is this form, integral, but this integral in specific form from a constant to variable x. Okay, that's why this is inverse. Okay, questions? And let's see. Okay. So if we assume this FTC 1, so this is FTC 1. If you assume FTC 1, fundamental theorem calculus 1, well, let's say this one. X is t. So by FTC, that is the x of f of x is actually meaning that this f is antiderivative of f. Antiderivative. What the antiderivative means? F prime equals f. Okay, and recall that any two antiderivative two antiderivatives only differ by constant. Okay. Let's see. That G the another antiderivative of f, say, then the difference f t is constant, right? Two antiderivatives differ by constants. Okay, so it's constant. Okay, let's write this down. See what the constant means. So for example, f is x, so is constant. All right, so let's put the, you would substitute x equals a. If you substitute, say constant c. If you plug in a, what you get here? Into a of a is just c. But this integral from a to a, meaning area from a to a, this always zero. Forgot to mention that. Okay, so meaning that c is minus g of a. Okay, so we know this is g of a, and if you substitute x equals b, what you have there? If you substitute b, what you have is from a to b g of b equals C also. But from here we know that A. Okay, so now what you have here. Then we write this down as equals to here, move it to G of B minus G of A. Okay, so what is this? And G is antiderivative of F. Okay, so this is what we call, in fact, what you know as the fundamental theorem of calculus. Second one is this. Let me just copy from oops. Second one. To write this down, just you see directly what we have so far. Oh, that's next chapter. Yeah. Okay. Okay, so this is the calculus. Okay, so this is the thing that you know from even from high school, how to compute definite integral. Okay, you find the antiderivative. Here you use G, use F, it doesn't matter. Any antiderivative. Here, see, any antiderivative. Okay, then you substitute B and A, find the difference. Okay. So in fact, this a fundamental theorem calculus first and second are actually equivalent, so they are the same. All right, we'll stop here, take a break, and then we'll continue with the proof and then examples, problems. All right, so let's stop the records now.